Hello, my brilliant students, and welcome. Today we are tackling a big one, a topic that is a guaranteed high score in your exams, organic chemistry. I'm telling you, whether you are writing WAEC, NECO, or JAMB, this topic will show up. So by the end of this lesson, you're going to feel confident and ready for any question they can possibly throw at you. Let's get started. Now, everything we are covering today is pulled straight from the official syllabus. No guesswork here. This is exactly what you need to know. We'll start with what makes the carbon atom so special. Then we're going to look at something called a homologous series and isomerism. After that, we'll dive deep into hydrocarbons and the key chemical reactions that you absolutely must have at your fingertips. So, are you ready? Let's jump right in. Okay, let's begin with part 1. Here, we're going to lay the foundation for everything else. You see, to understand organic chemistry, you have to first understand the superstar at the center of it all, the element carbon. So, what exactly is this organic chemistry all about? Well, to put it simply, it's the chemistry of carbon compounds. But have you ever wondered why one single element gets its own special branch of chemistry? It's because carbon has two unique superpowers, tetravalency and catenation. And these powers allow it to form millions and millions of different compounds. So here are the two words you need to lock in your memory. First, tetravalency. It just means carbon has 4 hands, so it can form 4 strong bonds with other atoms. And second, catenation. This is its amazing ability to link up with other carbon atoms, forming long chains, branch chains, and even rings. Honestly, these two properties are the entire secret behind the massive world of organic compounds. Now, to make sense of all these millions of compounds, we can't just study them one after another. No way. So we group them into families, and we call each family a homologous series. You can think of it like a human family with the same last name. Every member has the same functional group, which is like the family's character. It controls how they all react. They all share a general formula, and their physical properties, like boiling point, change in a very nice, predictable way. Look at this table. It shows it perfectly. Let's take the alkanes, for example. As we move from methane with just 1 carbon atom to ethane with 2, and then propane with 3, just look at what happens to the boiling point. You see that? It's steadily increasing. Now, why is that? It's because as the carbon chain gets longer, the forces holding the molecules together get stronger. Please remember this trend. It's a classic exam question. Okay, next up is a concept that JAMB just loves to ask about, isomerism. This is what happens when you have compounds with the exact same molecular formula, I mean the same number of the same atoms, but they are arranged differently. They have a different structure. Think of it this way. You have the same set of Lego blocks, but you can use them to build different things. The main types you see are chain, positional, and functional group isomerism. Let's look at a perfect example, C4H10. On the left side, we have butane, which is just a simple straight chain. But on the right, we have something called 2-methylpropane. And you can see it has a branch. Now, I want you to pause and count the atoms. Go on, count them. They are identical. Same formula, but totally different structures, different names, and even different properties. That, my students, is isomerism in a nutshell. All right, let's begin our tour of the different hydrocarbon families, starting with the simplest ones, the alkanes. Their general formula is CnH2n plus 2. Now, the key word to remember for alkanes is saturated. Saturated simply means they are completely full. They only have single bonds between the carbon atoms. And because they're already full, they can't add any more atoms. So instead, they undergo substitution reactions, where one atom basically gets swapped out for another one. And here is a classic example you must know for your exams. Methane reacting with chlorine. But look closely. This reaction only happens in the presence of UV light. That's the condition. What happens is one hydrogen atom gets swapped out for a chlorine atom and we get chloromethane. Please, don't ever forget the condition. That UV light is the key that makes it all happen. Next up, we have the alkenes with the general formula CnH2n. Now, unlike the alkanes, these guys are unsaturated. Why? Because they have at least one carbon-carbon double bond. This double bond is like a hotspot for chemical reactions. It's an area of weakness that can easily break open to add new atoms. And that's why alkenes undergo addition reactions. Now, this slide shows a very, very crucial chemical test. Let's say you are in the lab. How do you tell an alkane apart from an alkene? Simple. You use bromine water, which has a distinct brownish color. If you bubble an alkene like ethane through it, that double bond breaks, the bromine gets added across it, and poof, the brown color disappears. It becomes colorless. Alkanes can't do this because they don't have a double bond. This is a classic test for WAEC practicals, so pay attention. And finally, for this group, we have the alkynes. Their general formula is CnH2n-2. These ones are even more unsaturated because they feature at least one carbon-carbon triple bond. And you can probably guess, just like the alkenes, that triple bond makes them highly reactive and ready to undergo addition reactions. Excellent work so far. You're doing great. Now here, we're going to explore some other organic families and more importantly, see how all this chemistry applies in the real world, especially right here in Nigeria. You know, the key to identifying any organic family is to look for its functional group. The functional group is the special part of the molecule that gives it a unique chemical personality. For your exams, you absolutely must be able to recognize these three. The OH group for alkanols, alcohols, the COOH group for alkanoic acids, and the COO group for alkanoids, which you might also know as esters. Now, speaking of esters, one of the most important reactions you need to know is esterification. It's exactly what it sounds like, making an ester. You react an alkanoic acid with an alkanol, but you need a catalyst, concentrated sulfuric acid, and you get an ester plus water. Now, esters are famous for their sweet, fruity smells. When you smell things like pineapples, bananas, or even some perfumes, you are smelling esters. All right, let's talk about a very special case, the aromatic hydrocarbons. And the star of the show is benzene. Now, if you look at its formula, C6H6, you would think it's highly unsaturated and should be super reactive, right? But benzene's special ring structure makes it incredibly stable. And because of this stability, it actually behaves more like an alkane. It undergoes substitution reactions, not the addition reactions you'd expect. Please don't let the examiners trick you on that one. Let's talk about something big, literally big, polymers. These are giant molecules made from linking lots of small repeating units called monomers. Think of it like making a long chain out of tiny paper clips. There are two main ways to do this. In addition polymerization, the monomers just keep adding to each other, end to end. That's how we get polyethylene for our shopping bags. But in condensation polymerization, when the monomers join, a small molecule, usually water, is kicked out. That's how we make things like nylon. So, why is all this chemistry so important, especially in Nigeria? One word, crude oil.
Our crude oil is just a big, messy mixture of different hydrocarbons. We separate it into useful things like petrol for our cars, kerosene for our lamps, and diesel for our generators using a process called fractional distillation. And it works because of what we learned earlier about homologous series. The longer hydrocarbon chains have higher boiling points. So we just heat the crude oil, and the different parts turn to vapor and are collected at different temperatures. It's chemistry in action.
All right, are you ready? It's time to put all this knowledge to the test. This is the part you've been waiting for. We are going to solve real, actual past questions from WAEC, JAMB, and NECO. So pay very close attention to how I break down the steps. You can do this. Our first question is a classic theory question from WAEC back in 2011. It's all about conversions, a very, very common type of question. They want us to state the reagents we need to carry out these 3 chemical changes. Let's break it down one by one. Okay, for the first one, to turn ethene to ethanol, we need to add water across that double bond. This is called a hydration reaction, and it needs specific conditions, steam, and an acid catalyst like sulfuric acid. For part 2, to go from ethanol to ethanoic acid, we need to oxidize it. For that, you need a strong oxidizing agent like acidified potassium permanganate. And for part 3, we just saw this one. To make an ester from an acid, you need the matching alcohol, in this case, ethanol, and your concentrated sulfuric acid catalyst. That's esterification. You must master these conversions. Now, let's see what JAMB has for us. This is from 2010, and it's testing your knowledge of properties. Which of these compounds is very soluble in water? The secret to solving this question lies in a simple rule. Like dissolves like, and more importantly, something called hydrogen bonding. Okay, let's think about it. Water is a polar molecule. So for something to dissolve well in it, it should either be polar to, or even better, be able to form hydrogen bonds with water. Now, ethane and ethene are non-polar hydrocarbons, so they are out. The ester is only slightly polar, but look at ethanoic acid. That minus COOH functional group can form very strong hydrogen bonds with water molecules, pulling them into solution. That's why it's so soluble. The correct answer is A. Finally, let's tackle a question from NECO 2003. Now, don't panic when you see percentages in calculations. This is a very common question type, finding the empirical formula. And I promise you, it's just a straightforward step-by-step process. Okay, just follow me. Step 1. You take the percentage of each element and divide it by its atomic mass. For carbon, that gives us 2.44. For hydrogen, 5.7. And for bromine, 0.8125. Simple enough, right? Step 2. You look at those 3 numbers and find the smallest one, which is 0.8125. Now divide all 3 of your results by that smallest number. When you do that, you get a simple whole number ratio. 3 for carbon, 7 for hydrogen, and 1 for bromine. And the final step? Just write the formula. C3H7Br. See? Not so bad at all. Wow, we have covered so much ground today, and you have done a fantastic job sticking with me. Now let's quickly wrap things up by summarizing the most important takeaways. And then I'll share some of my personal top tips to help you crush this topic in your exams. Think of this summary table as your personal cheat sheet for organic chemistry. It has all the key families, their general formulas, and their most important features all in one place. I strongly suggest you take a screenshot of this right now for your final revision. Knowing this table by heart will fetch you some very easy marks, I promise you. And here are my personal tips for you. 1. Know your definitions inside out. What is isomerism? What is a homologous series? 2. Master the key reactions we talked about. Substitution, addition, esterification. Know them. 3.
practice naming compounds, and then it becomes second nature. And here's a special tip for JAMB, really focus on the properties and trends. But for WAEC and NECO, you need to be an expert on conversions, reaction conditions, and balancing the equations. And now, it's your turn to shine. Here are 2 challenge questions for you. One in the WAEC style and one in the JAMB style. I want you to apply everything you have learned today about functional groups and reaction types. Give them a serious try, and you can find the fully worked out solutions on the website. If you found this lesson helpful, and I really hope you did, please do me a favor, like this video, share it with your classmates and friends who are also preparing, and most importantly, subscribe to our channel right now so you don't miss the next topic. Also, make sure you visit examkp.com for thousands of free practice questions and answers. We're in this together. Let's smash these exams. I'll see you in the next lesson.